Hey guys, welcome back to day 13 of the One Quant Finance interview question every day. And today our question is actually a very classic JaneStreet question. So our question is horse race. There are 25 horses, each of which runs at constant speed that is different from the other horses. Since the track only has 5 lanes, each race can only have at most 5 horses. If you need to find the 3 fastest horses, what is the minimum number of races needed to identify them? So like usual, I want you guys to take around 5 to 10 minutes to think about this question yourself, and I'm gonna explain the solution in just a little bit. So for a problem like this, where at first we don't really know like how to start thinking about this type of problem. There isn't a formula that we can just directly use. So how do we approach this type of problems? Well, we can always start with like the most basic case. We're not trying to like find the best solution in just one step. Maybe we can start with some more intuitive solutions, right? So here's one of them, right? We got 25 horses. Why don't we label them through H1 to H25? And let's just say, just for the sake of our argument, H23, H24, and H25 are our 3 fastest horses that we're looking for. Oh my god, forget my handwriting. It's terrible. Okay. So, intuitively, if you're looking for the 3 fastest horses, maybe we can just, run it in different batches of fives. So let's just say we put H1 through H5 into one batch. So that's our first game. And then after first game, let's just draw let's use like people instead of horses. It's easier to draw. Here's your 5 horses or people. And then after each round, we take out the 2 slowest and we put in H6 and H7, and then we make a new race among the 5 fastest, the 3 fastest horse from round 1 and H6, H7. So just by repeating this process, we're able to cover all 25 horses eventually. And no, this is really intuitive, and it's definitely gonna guarantee our 3 fastest horses by repeating this way. So always keep the 3 fastest horse from each round, and then add in 2 more that we haven't raced yet. So eventually, on your last round, your 3 fastest horse will be the 3 fastest horses out of all the horses, and this is really intuitive. So how many rounds is this gonna take? Okay, so the first round we included 5 horses, and each of the following rounds we add 2. So 2, 2, 2, 2. So basically it's 5 plus 2n equals 25, and we know n is 10. So including the first round, we need 10 plus 1 equals 11. 11 total games to find the 3 fastest horses this way. And we know this is definitely not the perfect solution, but it is one of the solutions. But by doing this, we're definitely going to be able to find a solution. So here's why we always start with like the basic approach to it, because from the basic approach we can actually see some pattern. Okay, what is one pattern that we see? Okay, we are always discarding the 2 slowest horse from each batch. Why? Because we know we're only looking for the 3 fastest horses, and the 2 slowest from each batch doesn't matter. If they're not the 3 fastest, we don't need to worry about them. That's why we're always discarding 2 horses from each batch. And maybe we can use this idea to improve our algorithm. Okay, so how are we gonna do that? Okay, let's think about it. What is the usual format they do in like any sort of competition, right? Like the Olympics. So they do something called brackets. Maybe we can like use that idea from sports. Okay, so why don't we run all 25, 5 at a time, but we run all 25 in the first round. So we know like all 25 horses from each batch, we're gonna have a winner. So let's just say, for the sake of arguments, we put, we're gonna have H1 through H5 in this batch, H6 through H10, H11 through H15, H16 through H20, H21, H21 to H25. Let's just, for the sake of argument, this is our round 1. And here's our winner from each round. So, intuitively, if you want to find the fastest horses out of all 25 horses, we just need to put the 5 winners from each round and put them in a race. So this is our final. This is round 1. This is our final. So the winner out of these 5 will be the the H25 that we're looking for. The winner will be H25. So far we have gone through 6 games. And then that's our fastest horse. But how do we find the second and the third fastest horse? Because it's very likely that 3 fastest horses are going to be in the same batch on the round 1. So we can't just say the top 3 from the final will be our top 3 at the end, because it's very likely we are overlooking some scenarios. So why don't we take maybe the second place from each batch and put them in a race. So maybe for the sake of argument, it's going to be H4, H9, H14, H19, and H24. The second fastest from each batch of round 1. And the winner of this will be the fastest second place from round 1. So maybe that's going to be our H24. And then we can do the same thing for the third fastest. So maybe H3, H8, H13, H18, H23. And the winner of this is H23. So basically, we're running 2 separate races for the second fastest and the third fastest horse from each round. And what we want to do is we want to take these 2 horses, the winner from each, the second and third fastest horse, and we put them into the final, replace the 2 slowest horse in the final. And then we do 1 finale. And that's definitely gonna give us our third fastest horse. And how many rounds do we take? Okay, so in round 1, we have 5 games. That's our round 1. And then we did one final that allowed us to find our fastest horse, H25. And then we ran basically final, but for second and third place each respectively, which is going to be 2 games. And then we put in the winner of the second and third place. We put him in the same race with the originally top 5, except we removed 4th and 5th, and we replaced them with the 2 winners from our second and third place finals. So that's gonna have 1 more game. So how many games in total we have? We have 5 plus 2 plus 1 plus 1, and that's 9 games. Okay, so that's better than 11. We were definitely improving. But let's think about this process. Can we improve this algorithm even more? So the reason we did these 2 races for the second place final and the third place final is that we actually worry that there might be a case where H23, H24, H25, or the 3 fastest horse might be in the same batch in round 1, and by only selecting the fastest one from each batch and putting him in the final, we might actually be overlooking the H23, H24 that might be in the same batch. So that's why we are running 2 separate final races for the second finishers from round 1 and the third finisher from round 1. But do we really need 2 separate races? Let's look at this more carefully. Okay, let's say this horse who got 3rd in the final race. He was in the finale. He's the fastest horse from his batch, but he got 3rd in the final. But is there any need to check any other horses of his batch? The answer is no, because if you're the fastest out of all five of your batch, and you got a third in the final, that means the rest of the four horses from your batch is definitely gonna be slower. It's definitely not the three fastest horse that we really care about. So yeah, we don't really care about the batch that you came from. So we don't even need to consider them. So yeah, that logic applied to fourth and fifth place. If they got fourth and fifth place and they are the fastest from their batches respectively, their batches are definitely not the top three. The top three are definitely not in their batch. So yeah, so these batches we don't even look at them. But what really do need to care about is if this horse, my fault, if this horse is the fastest from his batch, but it's very likely that he could be the second fastest horse of all, but the third fastest also happened to be in the same batch. So we do need to take the second fastest horse of where this horse, the second overall finisher, came from, and consider him. So we basically take one other horse from the batch that he came from out. And then for the top finisher, we need to take the second and third place finisher from his batch and take them out. So now we put these 5 into a separate race. And that's actually going to be enough. Actually, I made a mistake. We don't need to take the fastest into a race. We do need to take the third fastest into a race. So we basically put these 5 into a race, and that's the top 2 finishers from this race. Is going to be our H24 and H23 that we're looking for. So with this algorithm, essentially we're not doing this final for second and third place anymore. Instead, we just need one more game. And if you count the numbers, it's going to be 5 plus 1 equals 7 total games. And 7 is indeed our optimal solution. So 7 games is the minimum number of races that we need to run to identify our top 3. So yeah. So the main difference between our second solution and the third solution is that our third solution uses a more clever algorithm, which considers the fact that the results from the final rankings actually tells us something about their respective batches. So therefore, we don't need to consider all the batches, only the batches that were the second and first place came from. That's where you need to pay extra attention to. So like usual, guys, I made a simulation on the problem that we just did. So here we actually have, the 3 algorithms that we looked at previously. And here, our first algorithm is where we kind of go through all of this, kind of brute force all of this, and we keep the top 3 from each round, and then we adding 2 more horses that we didn't look at. So like kind of the rolling top 3 solution. And so you can see here, we're always keeping top 3, and the last race is actually just going to give us the 3 fastest horses that we're looking for. So yeah, that's the brute force solution, and that's gonna definitely give us the correct answer in 11 different races. And let's take a look at the second algorithm that we used. So this is basically a combination of batches and brackets. So round 1 is our group races. We randomly divide horses into 5 different races, and we take the winner from each race, or the first place finishers from each group, and put them into the first place finishers race. And we know, just by intuition, the first place finisher out of this first place finisher race will be the fastest horse out of all 25. And then we actually go into each of the group races again, take out the second place and put in into a second place finisher race. Again, we repeat that for the third place finisher race, take out the third place finisher here, put them into a race. So, and we take the winner of the second place finisher race and third place finisher race into a final championship, put them with the 3 fastest first place finishers race and put them into a race. We'll kind of make this championship race, and the top 3 from the championship will be our top 3 of the entire 25 horses. And that's going to give us our correct answer in 25 runs. We can just run this again to see what it looked like in action. So nine races is going to give us the correct answer. And here's actually our optimal solution. So we would do the same thing for the group races, randomly divide them into groups of 5s, and then we do a championship race, or the first place finisher race. We're gonna have our fastest horse just decided from this, and then the key distinction is that instead of taking all the second place finishers, we only take the second place finisher where this second place finisher come from, or yeah, only where this second place finisher come from, the batch that this second place finisher came from. And then we take the second and third place where the winner came from. And we put all of them, so the second place, the third place from the championship race, and then the second and third place from this horse's batch, and then the second place from this horse batch into a candidate race for second and third. So the top 2 from the final candidate race will be our second and third fastest horse out of all 25, and combined with the winner of the championship race, that's going to give us our top 3. So this solution actually only takes 7 tries. So we can actually just run this again, but slow down so we can just see what it looked like in action. So yeah, that concludes our day 13 of doing one qualified and senior question. I'm actually gonna drop a link to the GitHub where I posted the code for the simulation. So yeah, if the video helped you, please drop a follow, and thank you for watching, and come back tomorrow for day 14.